All right, hello everybody, and welcome to Chapter 10 of Classical Dynamics of Particles and Systems. Looks like we're going to have a short chapter, so yay, I could probably do this one in one sitting, since Chapter 9 was on the longer side. That video was 2 hours long, so it's good to get a little break once in a while. Okay, so without further ado, let's get into Chapter 10, which is Motion in a Non-Inertial Reference Frame. We're going to be talking about rotating coordinate systems, centrifugal and Coriolis forces, and then motion relative to the Earth. So, let's get into the introduction. Okay, so basically the advantage of choosing an inertial reference frame to describe the dynamic processes we kind of saw in chapters 2 and 7, because it's always possible to express the equations of motion of your system in any inertial frame. But there are some types of problems where these equations get really complex, and it becomes easier to kind of treat the motion in a non-inertial frame of reference. So, let's say, for example, we wanted to describe the motion of a particle on or near the surface of the Earth. It's tempting to choose a coordinate system fixed with respect to Earth, and we know though that Earth basically goes a very complicated motion, different rotations, moving with respect to the Sun, and so forth. And hence, Earth's coordinate system is therefore a non-inertial frame of reference. And although we can get a lot of solutions to the problems by basically ignoring that and treating it as an inertial frame, we get a lot of important effects if we look into the non-inertial nature of Earth's coordinate system. We've actually kind of looked at this already when we did the ocean tides, if you guys remember back in Chapter 5. Because the tidal forces, the Earth, Moon, Sun, Earth orbits are a non-inertial system. So, let's look at a little diagram. So, here we have some coordinate system and then some other coordinate system. And the primes are the fixed system, and the non-primes are the coordinates of the rotating system. And we have some vector r, which just points to whatever point you're pointing at. So, basically, when we're analyzing the motion of rigid bodies, it's going to be kind of convenient to use non-inertial reference frames, and we're going to use a lot of the stuff we're going to talk about in 10.2. So, let's get into 10.2 though, which is rotating coordinate systems. I don't know if you guys can hear the helicopters. I don't know what's going on outside. Okay. So, it's considered two coordinate axes, which I think are in the diagram above. We'll say one is fixed, so the primes, or the inertial axis, and then we can let the other one be some arbitrary set that can move with respect to the inertial system. So we design these axes as the fixed and rotating axes. And if we choose some point P, like we do in this figure here, then we can define r prime in the fixed coordinate axis to be equal to r plus r, big R plus little r, right? Look at the diagram. So little r seems to be the r prime vector, basically, of the non-inertial system, and then big R is the vector that basically relates the two coordinate systems. Okay, so we can always represent arbitrary infinitesimal displacement by a pure rotation about some axis called the instantaneous axis of rotation. Sorry, you cannot spell. Instantaneous axis of rotation. Okay, so for example, if we have the instantaneous motion of a disk rolling down an inclined plane, we can describe the rotation about the point of contact between the disk and the plane. So if the system xi, our rotational system, undergoes an infinitesimal rotation del theta, which corresponds to some arbitrary infinitesimal displacement, then the motion of P, our point, which we consider to be at rest in our non-inertial reference frame, can be described as d theta cross r, where this r is in our non-inertial reference frame. And fixed basically tells us that this quantity dr is measured in our fixed coordinate system. And in other words, in our inertial reference frame, our x primes. Okay. Now if we divide this equation by dt, so I get dr dt fixed. Well, that's just d theta dt cross r again, which, remember, d theta dt is just theta dot, which is just omega. So therefore we have dr dt fixed equals omega cross r for some p fixed in xi in our rotational system, or rotational coordinate system. Okay. Now, if we allow the point P to have some velocity dr dt with respect to our coordinate system xi, then the velocity must be added to the omega cross r to obtain the time rate of change of r in the fixed system. In other words, if I have dr dt, again, in our fixed system, well, that's just dr dt in our rotating system plus omega cross r. Okay, so let's look at what this looks like in an example. So let's consider some vector r in the rotating system given by, this is a generic vector, x1, x2, x3. Let the fixed and rotating systems have the same origin, so I guess we're dealing with one of these systems, and the other system can be whatever. We want to find, basically, r dot prime in the fixed system by direct differentiation of the angular velocity in the fixed system. Okay, so let's, again, start with the fixed, and then let's take the time derivative directly. So it's just equal to the time derivative of the sum of the xi ei's, which from chain rule, right, is just x dot I ei plus xi e dot I. And then the first term is simply r dot r. Now this term right here, right, because it's just the velocity basically in that direction. But what are the e dots basically? We have to figure that out. So this r dot we can define as the dr rotating that we were talking about right here. So then we can rewrite this as r dot r, and then just leave the summation over these. And if we were to look at figure 10.2, let me just screenshot a bit more. Okay. And we examine the components of omega I that tend to rotate with E1. We see that omega 2 tends to rotate with E1 toward the minus E3 direction, and that omega 3 tends to rotate towards E1 in the plus E2 direction. So therefore we have the derivative of E1 with respect to t. So how this vector E1 changes is going to be given by omega 3 E2 and then omega 2 E3. Okay. And that's because of the cross product, I think, actually. Let me double check to make sure it makes sense. So I have this vector, and actually, let me just do it with my hand. I just use the right hand rule. Yeah, if you use the right hand rule, the ones that point in the one direction are basically the cross terms. Like if you were to take a determinant. Okay, likewise, we get the exact same thing with E2 and E3. In each case, okay, yeah, perfect. It tells us it's the cross product. Okay, yeah. The directional time derivative has to be perpendicular to the unit vector in order to not change its magnitude. So we can write them as so. And then we can basically rewrite our dr dt fixed as I remember r dot r, and this is in the rotational frame, plus sum over I omega cross xi ei, which is just equal to r dot r plus omega cross r, which is the same result as up here. So we saw that we get the same thing. So although we chose our displacement vector r in our derivation of 10.6, 10.6 is this equation right here basically that we just re-derived in the example. It's not just limited to the vector r. In fact, this works for any arbitrary vector q. That's an important result. So for example, if the angular acceleration omega dot, or alpha, is the same in both the fixed and rotating systems, sorry, it is the same because if you do omega cross omega, well, any vector cross itself, right, is just 0. So that means the angular acceleration in both systems is fixed. Okay, so now we can use our equation 10.12 right here for the arbitrary vector q to obtain the expressions for the velocity of the point P as measured in the fixed coordinate system. So from equation 10.1, we have our fixed is equal to our r, which is, this vector r, remember, relates the two coordinate systems, and then this vector r is like from the non-prime system, from the rotating system. It's where P is located from its origin. Okay, so we can define V final as r dot final, which is just our, or sorry, V fixed is probably what they're talking about. Yeah, fixed. As just dr dt, so it's this right here, and then we have capital V is just the relationship between the two coordinate systems, and then VR is our rotating frame, and then if we plug that into our equation here, we get V fixed is equal to big V plus V rotating plus omega cross r, just from our equation 10.12, and I guess here are their definitions of it, which I think I kind of already said. Relative to the fixed axis, linear velocity of the moving origin, which is just, remember, if we have two coordinate systems, I'll draw in 2 dimensions like that. It's just the vector that relates the two. Relative velocity relative to the rotating axes, and we have the angular velocity of the rotating axes, and then omega cross r is the velocity due to the rotation of the moving axes. Okay. So that was a lot of, I guess, just terminology, really. So now I can move into actually seeing the use of this in 10.3, when we're going to talk about centrifugal and Coriolis forces. Okay. So we know that Newton's laws, right, like F equals ma, is only valid in the inertial frame of reference. So, therefore, the expression for the force on a particle can only be obtained from the fixed, right, the time derivative of the fixed coordinate system. That's why we have VF, where we have to basically differentiate with respect to the fixed system. So if we were to differentiate 10.17, this equation right here, we basically have dVF dt fixed is equal to all with respect to fixed, basically, is the point. And we can call the first term right here just big R double dot fixed, because remember, this V comes from the R, it comes from dr dt, which is the relative velocity between the two coordinate systems. And then the second term right here, we can evaluate if we substitute in VR for Q in equation 10.12. So 10.12, remember, was just basically the equation we got before, all the way up here, just with an arbitrary vector Q. And if we were to plug that in, we get the fixed version is just the rotating plus omega cross VR, which is just equal to our acceleration rotating plus omega cross VR. And then the last term, right here, we can get directly from our earlier equation, which is just I'll just screenshot actually. The last term just goes straight to this. So we have omega cross dr dt fixed is just omega cross dr dt rotating, because we're just taking the fixed, moving it to the rotating, and then crossing it with the cross product, right? And then if you do that using vector identities, it simplifies to this right here. So we can combine these equations then into one big equation for Newton's second law, which tells us that F is equal to ma, right? And if we were to plug in our values, we're left with this big expression for, that correspond to all of these. But now, for an observer in the rotating coordinate system, the effective force on the particle is given by MAR, because he's in the rotating system, which is just equal to, if we just basically take out MAR from this equation, we can write it in terms of the force. So all we did basically is we moved MA over here and moved F there, like quite literally. We get this expression here. Where, remember, F is the sum of the forces acting on the particle as measured in the fixed system. So remember, this is fixed. And this MRF and M omega dot cross R exists because of the translational and angular acceleration of the moving coordinate system relative to the fixed. And then this M omega cross R right here is the centrifugal force term, and reduces to the usual like mv squared over r, or m omega squared r, when omega is normal to the radius vector. And then notice that there's a minus sign because it implies that the centrifugal force is directed outwards from the center of rotation. And the last term, this 2m omega cross VR right here, is this new term called the Coriolis force. Okay, now this arises from the motion of the particle in the rotating coordinate system, and because the force is proportional to VR, right, it vanishes if there's no motion, so we're left with our normal expression in like an inertial reference frame. So since we've used the term centrifugal force, and we've now introduced the Coriolis force, we now need to kind of look deeper into what the physical meaning of these quantities are. So basically, we need to realize that the centrifugal and Coriolis forces are not forces in how we normally talk about forces, because they're kind of artificial forces that we write because we want to be able to write an equation that looks like Newton's law and have it valid in a non-inertial reference frame. So let me show you guys a picture. So this is kind of what we were just talking about. We have that omega cross r points outwards, and then if we add a mass here, we basically get the usual centrifugal force, which again we see it points radially outwards, which is what we were talking about. And yeah, so basically the reason why we have this Coriolis force and centrifugal force is because we're basically asserting we need to have a Newton's like law equation, which is only valid in an inertial frame. So in a rotating frame, we basically want to get our force effective, which is just ma rotating, if we let r double dot fixed equals 0 and omega dot equals 0. And then we can express this equation in terms of the real force MAF as our force effective is equal to MAF, this right here, plus non-inertial terms. And that's where our non-inertial terms we identified as the centrifugal and Coriolis forces. In other words, they're not real forces in the sense of how we usually identify a force. So if a body is rotating about a fixed force center, the only real force on the body is the force of attraction toward the force center that gives you the centripetal acceleration. But an observer moving with the rotating body, however, measures the central force and notes that the body does not fall towards the force center. So in order to kind of reconcile this fact, since we need the net force in the body to vanish, the observer basically sees the centrifugal force, which is what points outwards, right? So in reality, this is your real force, and then, but if you're like the person here rotating, you kind of feel this force, so you feel both basically. Now, this requirement is basically artificial because it's just a way that we can use to mathematically describe the system in a non-inertial system to use Newton's equations, and it's basically a correction force. Now, we can say the same thing for the Coriolis forces, which arises when we want to make an attempt to describe motion relative to a rotating body. Despite the fact that these aren't real forces, they're pretty useful because to describe the motion of a particle relative to a body rotating with respect to an inertial reference frame is very difficult, but we can make it pretty easy if we just lump in these non-inertial forces, which then we can just plug and chug Newton's equations. Okay, so let's look at an example. So we have a student is performing measurements with a hockey puck on a large merry-go-round with a frictionless horizontal flat surface. The merry-go-round has some omega and rotates counterclockwise as seen from above. Omega. We want to find the effective force on the hockey puck after it's given a push, and then plot the path for various initial directions and velocities of the puck as observed by the person on the merry-go-round that pushes the puck. So the first three terms in our force effective equation in 10.25, remember guys, 10.25 was the long equation for F right here. Sorry. So the first three terms are equal to 0. And then we can just write it as just the last two terms, which is just our centrifugal and Coriolis force. And remember, frictionless, so we take the friction force to 0 because it's a smooth surface. And VR is the velocity as measured by the observer on the rotating surface. So then our effective acceleration is we just divide by the mass from Newton's laws, and we just immediately see the masses just go away, and we're just left with these cross products, which we can basically get from integration of the acceleration. Okay, so we basically put the origin of our rotating coordinate system at the center of the merry-go-round. So our origin is, right there. And we basically need the initial positions and velocities of the puck to plot the motion. So in this example, we're going to let the radius of the merry-go-round be r. Actually, I don't know why I'm drawing stuff, because they draw it for you, and their drawings be much better. And then we're going to let the puck always start at negative 0.5 r and 0. So let's see what that looks like. Oops. Let me just screenshot the... So remember, guys, everything's rotating like that. Okay. So we basically want to compare the paths now, and see what's happening. So in each of these cases above, the puck moves in a straight line in the fixed system because there's no friction or external force in the plane. But since it's rotating as well, the merry-go-round, or the whatever it's called, the place where the ice is, we get these different shapes. And we see as we decrease the velocity what happens. And we're left with these systems here. Okay. Okay. Let's get into the last section of this video, which is 10.4, motion relative to the Earth. Okay, so the motion of Earth with respect to an inertial reference frame is dominated by Earth's rotation about its own axis. So the effects of other motions, you know, like revolving around the sun and the motion in the solar system, while you guys probably have heard crazy numbers about how fast the Earth, right, is moving, like in the sky, basically. We always kind of ignore those on Earth. That's because they have a very small effect in comparison to Earth's rotation about its own axis. So if we were to place a fixed inertial frame at the center of the Earth, and then a moving reference frame on the surface of the Earth, we can now kind of describe the motion of moving object close to the surface of the Earth, as shown in this figure here, 10.5. So we have our fixed, right, is like the center of the Earth. So this right here is our Earth. You know, I can't really draw, but pretend this is like 1 octant of the sphere. Okay, and then we're placing our moving reference frame on the surface of the Earth, basically. Okay. We can then apply our equations to basically get the dynamical motion, and we can talk about the forces in the fixed inertial system as F is equal to S plus mg naught, where S is basically the sum of external forces. Stuff like impulse, friction, electricity, magnetism, whatever, right? And then mg naught is the gravitational attraction to Earth. And then where g naught is given by you know, the usual negative gm over r squared. Okay. So we're basically going to assume that the Earth is spherical, which to a very good approximation it is. It's not actually perfectly spherical, but whatever. Which we saw in the tidal stuff, right? We saw how the Earth stretches. And we're also going to assume it's isotropic and that r originates from the center of the Earth. And then the acceleration of gravity varies over the surface of the Earth due to Earth's oblateness, density, non-uniformities, and altitude. So we're going to choose right now to not basically look at this complexity and motion relative to Earth, but we could basically look at these effects when you do a computer calculation. So let's look at the force effective. If we use our F is equal to S plus mg naught and plug that into our force effective equation, where remember it's just we just substituted in F is equal to MAF, and then we took the MAF here and just put in the F, where the F is just S plus mg naught. We get this expression here. And we can let Earth's angular velocity omega be along the inertial system's z prime direction, so right here. And we know the value of omega is 7.3 times 10 to the negative 5 radians per second, which seems pretty slow, but it's actually 365 times greater than the rotation frequency of Earth around the sun, year, right? Then the value of omega is practically constant in time, so we can kind of ignore omega dot cross r. So we can ignore this right here. And then what we can see here is that this r double dot final is just omega cross r dot, fixed, not final, sorry. So then r double dot f is just equal to omega, doing it again, omega cross r. So then we can rewrite equation 10.3, neglecting the first term and performing that substitution as so, and the second and third terms, basically if we divide by the mass, right, is basically what we feel in measure on the surface of the Earth as the effective G. So notice it's not G dot, it's a G, where G is equal to G naught minus omega, minus omega cross R plus R. All these are vectors, but whatever. These are all vectors, actually. And we basically call it G. Now, the second term, and this equation right here, is the centrifugal force. And because we were limiting our calculations near the surface of the Earth, we know that R is much, much less than R. Little r is much, much less than big R. So the omega cross R, so we can kind of ignore the little r, basically, is the point, is the part that's actually contributing the most to our G vector. However, if we're very far away from the surface of the Earth, we'd have to consider both omega cross little r and omega cross big R. And then this centrifugal force is responsible for the oblateness of the Earth. And since we know the Earth is not really a solid sphere, right, it's basically a strongly viscous liquid with a solid crust. And because of Earth's rotation, it's kind of deformed so that its equatorial radius is 21.4 kilometers greater than its polar radius. So it's kind of I'll draw it's not a perfect circle, it's more like a thick circle like that is how I would describe it. This is a note. Oops. Okay, I'll do it this way. Not to scale. Notice that this is much wider, right? This is the perfect sphere case. Now, that tells us, if we were to do the math, that the acceleration of gravity is actually 0.052 meters per second squared greater at the poles than at the equator, right? Because our R is less. And then the surface of a calm ocean water is perpendicular to our G vector, not G naught, and the plane of Earth's surface is also perpendicular to G. So G is the vector that really matters. So we can rewrite our equation for force effective in a more simpler manner just putting in a value for g, not g naught, as so, which we're going to use this equation to discuss the motion of objects close to the surface of the Earth. So remember, this is all an approximation close to the surface of the Earth. So let's look at the period of a pendulum, which can determine the magnitude of g. And then the direction of a plumb bob in equilibrium determines the direction of g. So let me just screenshot this. Okay, so let's look at this diagram. So we're given some value for omega squared r. So we determine the direction of the centrifugal term by this omega cross r plus r. And remember, the centrifugal term is in the opposite direction of that because it's outwards, which we can see here. So we see g naught points how you'd expect towards the center of the Earth, but the actual g vector does not, and the actual g vector is what we feel. Again, this is exaggerated. Obviously, it's not that big of a difference, but near Earth's surface, g naught makes up basically almost all of g. But as we get farther away, we care more and more about this centrifugal term. So let's look at, in the northern hemisphere, if we have a particle projected onto a horizontal plane, it will be directed towards the right of the particle's motion, and the southern hemisphere will be directed towards the left because of this cross product. Okay, so now let's look at Coriolis force effects. Okay, so the angular vector omega, which represents Earth's rotation about its axis, is directed in the northerly direction. So in the northern hemisphere, omega has a component, omega z, directed outward toward the local vertical. And that means if we project it onto a horizontal plane in the local coordinate system, basically on the surface of the Earth, with some velocity vr, then the Coriolis force is given by negative 2m omega cross vr. In other words, it has a component in the plane of magnitude 2m omega z vr. Okay. And if we look in this figure, that tells us that in the northern hemisphere, it's directed towards the right of the particle's motion, and then if in the southern hemisphere, right, it just flips and it goes to the left. And that's because in the southern hemisphere, the component of omega z is directed inwards along the vertical, so it's opposite. Now, the most noticeable effect of the Coriolis force is that on like air pressure, basically. So as air flows, we know air goes from high to low, right? Pressure. The Coriolis force deflects the air towards the right in the northern hemisphere, producing cyclonic motion. So making like cycles, basically. Like so. And then, what's it called? And we notice that the rotates with high pressure on the right and low pressure on the left. And the high pressure basically prevents the Coriolis force from deflecting the air masses farther to the right, which results in a counterclockwise flow of air. Okay. And then in more temperate regions, the airflow does not really go along pressure gradients, but rather along the pressure isobars due to the Coriolis force and the associated centrifugal force of the rotation. So what this is saying basically is that depending if you're in the north and south, basically the air will rotate differently depending on how far away you are from the equatorial regions. So if we're near the equatorial regions, right, then the sun, it's very hot. The sun heats the Earth's surface, which causes hot surface air to rise. And then in the northern hemisphere, that means cooler air moving in a southerly direction towards the equator. So then the Coriolis force deflects this moving air to the right, which is how we get trade winds, which basically give you a breeze towards the southwest in the northern hemisphere. So, oops, wrong thing. Let me just draw a diagram. Okay, so we know northeast, southwest. That tells us these trade winds. The Coriolis force moves the air to the right, which basically gives us a breeze this way. And this effect doesn't really happen at the equator because the directions of omega and v. So it's actually a lot more complicated than in reality than just taking into account the Coriolis force, but to a good approximation, just looking at the Coriolis force, you basically get the net effect of what's actually happening with trade winds and stuff. Okay, so let's look at an example, because that probably is very complicated. Okay, so we want to find the horizontal deflection from the plumb line caused by the Coriolis force acting on a particle falling freely in Earth's gravitational field from some height h above the Earth's surface. Okay, so we're going to use equation 10.34. We're going to set the other forces like impulse, electromagnetism, and all the other stuff to 0. Then we could set the force effective to just MAR, or R is the rotational acceleration, given by G minus 2 omega cross VR, since S again is 0. So then the acceleration due to gravity, G is the effective one and is along the plumb line. So we can choose the z-axis going vertically along basically minus G, like so. So here's our z-axis. Okay, and this is just, I guess, a diagram of the falling particle from the plumb line caused by the Coriolis force. And then, with our definition, right, of EZ, which points along negative G, we can basically construct the right-hand coordinate system if we specify EX to be in the southern direction, like so, on the surface of the Earth, and then EY obviously is perpendicular to that, like so. So we can make the approximation that the distance of a fall is sufficiently small that G remains constant during the process. In other words, H is much, much less than the radius of the Earth. Okay. Now I've chosen the origin of the rotating coordinate system to be in the northern hemisphere. So we have omega x is equal to negative omega cosine lambda. If we just look at this vector here, right? Okay, so in the x direction, we have omega cosine, and the y direction, they're perpendicular, so it's 0. And then in the z direction, we have sine, right? Let me just draw it out so I know it makes sense. Omega EZ, like so. This right here would be lambda. So it is. Okay, wait. So sine lambda is equal to omega over EZ. So then omega is equal to sine lambda EZ. I mean omega, sorry. Not omega Z, not EZ. Yeah. Okay. So then the Coriolis force produces some small velocity in the EY and EX directions, and we can neglect x dot and y dot when we compare it with z dot. So then we can basically say that z dot, basically the net effect is just negative GT, right? Where we basically get z dot if we consider just something falling from rest, right? So it's just v is equal to at, v naught is equal to 0, a is negative g. So we can calculate the cross product just by taking the determinant, and we get minus omega gt cosine lambda ey. And then we can get the components of g as gx is 0, gy is 0, and then gz, the direction you're falling in, is negative g. So then the components of ar, we're neglecting terms in omega squared, are basically in the x 0, and the y 2 omega gt cosine lambda, and the z is just negative g as expected. So basically the Coriolis force then is what's actually producing this acceleration in the y direction in the easterly direction. And if we integrate twice, right, we integrate this twice, we get 1/3 omega gt cubed cosine lambda, where if we set the initial conditions to be 0, then the integration of z dot basically gives us the expected distance of the fall. Okay. Which I got cut off. That's 1/2. Sorry about that. And then we can get again, expectedly t is basically square root 2h over g, just classic kinematics. So then the distance for the eastward deflection is approximately 1/3 omega cosine lambda 8h cubed over g. So an object dropped from a height of 100 meters at a latitude of 45 degrees is deflected approximately 1.55 centimeters eastward due to the Coriolis force. So it's a very small effect, I would say, but it's not negligible. Okay, let's look at one more example. Okay, so to demonstrate the power of the Coriolis method for obtaining the equations of motion in a non-inertial reference frame, let's look at the last example but use just basically central motion stuff. So we're going to ignore the Coriolis force. So let's release a particle of small mass m from a tower of height h above the Earth's surface, and the path of the particle described as a conic section, an ellipse with epsilon about 1, and the one very focused very close to Earth's center. So if r is Earth's radius and lambda is the northern latitude, then the moment of release, the particle has a horizontal velocity in the eastward direction, given by r omega cosine lambda, which r is given by r plus h, where again, h is much, much less than r. So the angular momentum about the polar axis is just mrv, right? And we plug that in, and we get this expression here. And then the equation of the path, if you guys remember from previous sections, is, I think it was like chapter 8 or something, alpha over r, which is equal to 1 minus epsilon cosine theta. So then if we measure theta from the initial position of the particle, let me show you what that looks like. Theta is this angle right here. And that's the path the particle takes. We see again it's deflected eastward. Then at time t is equal to 0, we have alpha over r plus h is equal to 1 minus epsilon, just by plugging in basically cosine theta is, cosine of 0 is 1. Okay, and then plugging in r is equal to r plus h. So you can rewrite this equation right here as to solve for r. And then if we want to basically get, again from chapter 8, the aerial velocity, we get 1/2 r squared d theta dt is equal to 1 over 2m. And now if we let theta equal to theta naught when the particle has reached the Earth's surface, so r is equal to r, then we can rewrite our equation in terms of theta naught. And if we invert it, we're left with this expression here, 1 plus 2 epsilon over 1 minus epsilon sine squared theta naught over 2, which lets us solve for the ratio of h over r. And then because the path described by the particle is almost vertical, that tells us a little change occurs at the angle theta between the position of the release and the point at which the particle reaches the Earth's surface. In other words, theta naught is therefore small, because because remember, we're saying theta starts at 0, and therefore sine of theta over 2 basically can be approximated as so, with an expansion. And then we can expand in the integrand, plugging in, remember, our angular momentum equation, and getting t is equal to 1 over omega cosine lambda, 0 to theta, d theta, our expression over here. And because theta is small, right, we can simplify this again into how we did over here. And then solving for the total period of time, since we're integrating from 0 to theta naught, we're left with this expression here, 1 over omega cosine lambda, 1 minus 2h over 3r theta naught, and we can solve for theta naught again, and we get omega t cosine lambda 1 plus 2h over r. But during the time it takes basically to fall, the period, Earth turns with an angle omega t, so the point on Earth's directly below the initial position of the particle moves towards the east by an amount r omega t cosine lambda, and then during that same time the particle is deflected toward the east by an amount r theta naught. So that tells us that the net easterly deviation is this r theta naught minus this, basically how much the Earth has moved, which is 2/3 h omega t cosine lambda. And again, using basic kinematics, t is equal to square root 2h over g. We finally get d is equal to 1/3 omega cosine lambda square root of 8h cubed over g, which is the exact same example we got in the previous problem, just much faster, right? Okay, so that should probably demonstrate the power of the Coriolis force. Okay, let's finish this video off with one more example. So we basically want to find the effect of the Coriolis force on the motion of a pendulum producing a precession or rotation with the time of the plane of oscillation. So it's called a Foucault pendulum. Not sure if I'm saying that right. Okay, so let's try to finish this video in under an hour. So to describe this effect, let's choose some coordinate axis with the origin at the equilibrium point of the pendulum and the z-axis along the local vertical. So we only care about the rotation of the plane of oscillation. That is, we basically want to consider the motion of the pendulum bob in the xy plane, the horizontal plane. So therefore, we limit the motion to oscillations of small amplitude, with the horizontal exertions small compared to the length of the pendulum. So under this condition, basically, z dot is very small compared to x dot and y dot. We're just going to neglect it. So we have in the rotational frame, AR is equal to g plus t over m minus 2 omega cross VR, where t over m is the acceleration produced by the force tension T of the pendulum. So we basically have these expressions for tension and x, y, and z. And again, same expressions for g and omega. And then we can look at the geometry for the focal pendulum. And we see again that g points along the minus z direction. And then the tension T basically separates into Tx and Ty since it's rotating. And that lets us then write then that Vr with respect to x is just x dot, Vr with respect to y is just y dot, and Vr with respect to z is just z dot, which is basically 0. Right, since it's not going to be moving up and down, right? It's very small compared to this kind of motion, like that in the plane. Okay, so we can take the cross product of omega cross v, using, again, basically treating it as a determinant, and we get in the x, y, and z these expressions in terms of y dot and x dot, and then the equations that we actually care about are the accelerations in the y and x, which if we plug in, we get these expressions here. And then if we have very small displacements, we can basically say the tension is approximately mg, and then we can define alpha squared to be equal to T over ml, which is approximately g divided by L. And then since we know that omega in the z direction is equal to omega sine lambda, we can basically write our equations of motion for the x and y direction as so. And what we notice here is that x double dot and x give us an answer in terms of y, right? And then y double dot plus y gives us an answer in terms of x, and these are what's called coupled equations. So the x and y motion is coupled together, and we can basically get a solution by adding the first of the above equations to I times the second, as shown here. So basically make one imaginary, and we can basically write q as the imaginary term, and then we're left with what looks like a more complicated version of a harmonic oscillator, which is the damped oscillations, right? And then the term corresponding to the damping factor is entirely imaginary. So we can basically get the solution from chapter 3 a long time ago. And basically it tells us if the Earth was not rotating, then the equation for Q would just be the simpler case, which is the exact oscillation frequency of the pendulum. But this frequency already is so much greater than the angular frequency of the Earth's rotation. So basically this tells us that even if you were to take into account Earth's rotational motion, it doesn't change the period of the pendulum much. And we see if we do the math, we get the equations for x and y, and then we can basically write it as the rotation matrix, which gives us a clear demonstration of the rotation of the Earth. So okay, I actually have to go now, so kind of wrapped it up pretty fast. Sorry about that, but thank you guys for watching, and I'll be doing chapter 11 next time, and hopefully I'll be feeling better, so I won't rush so much. All right, see you guys.